Hello, my name is Peter Van Horn. I am with Derek Bellinger and Aaron Keeter to present our ELEN498 Senior Seminar Design Proposal, Autonomous Metal Detector. This project addresses the problem of how to completely scan a user-defined area for metal objects efficiently with minimal operator intervention. To that end, the specifications of the end product are as follows. The solution consists of a mobile rover capable of autonomous action and a controller by which the operator interfaces with the rover. The rover must be able to detect metal objects and be able to report locations within 12 inches of the object's location. It must be able to cover 100% of the operator-defined area with exception to passable terrain such as trees, furniture, walls, and other navigation hazards. The rover must be powered by a battery pack. The vehicle will be fabricated from wood and plastic materials readily available from the local hardware store, as well as project kits such as a tank chassis. The rover is intended for outdoor use in dry conditions. It will not be waterproof and should be able to be operated between 32 degrees and 125 degrees Fahrenheit. The controller will be a laptop computer with Wi-Fi capability. The operation of the system is as follows. Turn on the rover, connect the computer to the rover over Wi-Fi, and start the control program. The operator directs the rover to record a start location, then manually directs the rover to locations along the perimeter of the desired search area, recording waypoints at the turns along the perimeter. After the final waypoint is recorded, the operator instructs the rover to initiate the search. The rover will immediately pursue the first waypoint, recording and reporting the locations of any metal objects detected. At any time during the search, the operator may abort, causing the rover to disregard remaining waypoints and return to the start position. When the search is complete, the rover will return to start position and await further instructions. The rover can then be directed to pursue locations of detected metal objects. Once the detected object is resolved, perhaps by collecting or ignoring, the item is dismissed from the list. After all items on the detected object list have been dismissed, the rover is powered down, control program stopped, and operation of the autonomous metal detector system is complete. Agency approvals required are Federal Communication Commission for Wireless Communications and Underwriters Laboratories for battery charging equipment. These will be obtained through use of pre-certified equipment. The project cost estimate for research, development, and assembly is $1,000 with a manufacturing cost of $100. This concludes the problem statement.
Hi, this is Derek Bellinger. Our main deliverable, of course, is the autonomous metal detector, which is in the form of a rover, um, and it's part of the system that consists of a rover interface, the rover itself, and a laptop computer for the operator to control the rover. Our list of deliverables for the rover is the wiring schematic, and the wiring schematic is pretty self-explanatory. It will show the setup of all the components and how they're wired together to the Rio, which is controlled by the program we're going to be creating in LabVIEW, um, which is all controlled by the operator. And there's an operating guide we will be developing for the rover, so any operator can come in and do their own search for metal objects and set their own waypoints, but it'll also have troubleshooting and risks involved.
The following items are anticipated for the different components of this project. For the rover, the body will be constructed of medium density fiberboard assembled using wood screws and wood glue and painted with a multi-surface primer and exterior barn and fence paint. The onboard computer will be the National Instruments MyRio. Peripheral attachments to the MyRio will be the Diligent MXP breadboard adapter, Diligent motor adapter, and 400-point solderless breadboards. Electrical connections will be made between components using male-female, male-male, female-female, and U-shaped jumper wires. Propulsion system will consist of two DC motor gearboxes from the mechatronics kit and a tank tread track system. Several different sensors will be used. Location sensors will be constructed from PMOD gyro, PMOD compass 2, and PMOD GPS. Navigation sensors will include PMOD max sonar, IR range sensor, and push buttons. The metal detector will be constructed using on-hand resistors, capacitors, rectifiers, MOSFETs, bulk wire, and Hall effect latches. The rover's power plant will consist of one 12-volt nickel metal hydride battery pack. Backup power will be a spare battery and a universal battery charger. This completes the materials list for the rover. The controller will be a Windows 10 laptop PC with LabVIEW 2019 MyRio real-time software. The total cost projection, including items on hand, is $989.01. Current out-of-pocket expenses is expected to be $155.51. This concludes the bill of materials.
Hello everyone, my name is Aaron Keeter. The first thing I'll present is the Gantt chart that should keep us on track for the duration of the project in the actual course of ELEN498. First you can see the project leads at the top. Below that you can see the budget. Below that it gets into our timeline that we wish to hold to keep us on track to complete the rover, as we're calling it, by the end of the course. We're starting with the sensor system design and prototype. With that, the metal detection, obstacle detection, and the coordinate system. We're starting that right at the beginning of the course on September 2nd and ending on the 29th, giving ourselves 28 days to complete the design and prototypes. Next, we have the equipment design and prototype. With that, the rover and controller. We're going to be starting this on the 16th of September and ending on the 13th, also giving ourselves 28 days. We understand the overlap that we have created here, but we're confident that this will not degrade the final project, and we can handle the task at hand. Once these are complete, we'll begin testing and revision for the rover. Each component will be tested individually, and then as we put it together, we will be testing the system as a whole. We plan to start these tests on the 23rd of September and end on the 1st of December. If all tests are successful without any issues, we'll be compiling our presentation on the 2nd of December and hopefully presenting it and approved by the 22nd of December. And that should complete our senior seminar project. To the right of that, you can see a visual for the timeline I just outlined briefly for you guys to keep us on track for the duration of ELEN499.
Hello again and welcome back. My name is Derek Bellinger and I'm presenting the block diagram portion. Let's jump into it. So here you can see our block diagram. There are 7 feedback devices that will be reporting through the MXP to the MyRio, which will be powered by the 12 volts DC power supply, which will also be powering the motor adapter, DC motor gearbox. The MyRio will be operating through Wi-Fi via the laptop PC, where the operator will provide all the inputs and controls for the whole process. Starting with the MyRio accelerometer, it's going to be measuring the acceleration in 3 linear axes. The bumper sensor will just detect when we bump into something. The IR rangefinder will hopefully tell us the range between our rover and any objects. The metal detector will detect metal. The gyroscope will be reporting radial acceleration and how fast we're changing speed through turning. The compass is just a magnetometer. And the GPS will be recording when the location when metal is detected and helping us to plot where our rover is going.
The program for the autonomous metal detector is performed in 3 stages: initialize, search, and resolve. The initialize stage performs the power-on self-test to detect any errors and calibrate sensors such as the metal detector. After startup is complete, the operator provides the search area definition. Search phase is performed autonomously by the rover, using the perimeter of the search area as the initial navigation waypoints and updating the list of waypoints until the search area has been traversed. During the search phase, the rover scans for metal objects and records the location of any detection event. When the search is complete, the rover returns to start position. The resolve phase is performed with the operator. The rover may assist the operator in returning to the detection sites to resolve objects found. After all detections are resolved, the rover powers off. During the initialize and resolve phases, the rover is under the operator's control. During the search phase, the rover operates autonomously. This concludes the description of the software flowcharts.
Hello everyone, this is Aaron here again, and now I'll be presenting the test plan for our final project. The first test we will be conducting will be the metal detector sensitivity test, and this test will be to determine the most efficient voltage to range for the metal detector. Test number 2 will be the proximity sensor function test, and this is to help us determine the placement criteria for the proximity on the actual device. Scroll down a little bit, We'll also be doing the communications test. This will help us determine the distance at which the rover will lose communications with the controller at a wireless standpoint. A little bit further down, we have the automatic drive test. We're going to be doing this test twice, without and with obstacles. And this is just to help us determine if the device functions as designed, and that is to avoid obstacles. Further down, we have the terrain test. We'll be testing this device on mostly smooth terrain, such as a sidewalk, freshly cut lawn, football field, and a track. We just want to make sure that it navigates easily accessible areas, near residential areas, things of that nature. We'll also be conducting 2 metal detector tests. Each one of these will be on the different types of terrain that we discussed earlier. The first one being on a track or a driveway, kind of like a hard packed surface, and the next being on a lawn or a football field. And we just want the rover to detect and then report back to the actual controller. The last test we'll do, test number 12, will be the endurance test, and this is to determine maximum search time on the battery. Pretty much just a battery life test. Make sure we're not just putting out a 3-minute metal detecting rover. Hello everyone, this is Aaron Keeter again, and I will be presenting the alternate approaches section of our final project presentation. The first alternate approach has to do with the MyRear failure. If this occurs, our alternate approach would be to use the Arduino or Raspberry Pi to control the system. The second alternate approach has to do with the MyRio being realized that it's not sufficient enough to control all the devices that we're attaching, the sensors, the metal detection system, the GPS system, and whatnot. And we might ask the assistance of the Arduino or the Raspberry Pi. And if those don't work, we might replace the MyRear controller entirely with another version. Another alternate approach has to do with the drive motors being insufficient to complete or power the rover. A workaround for this could be to remove all the inconvenience items, replace components as well with lighter versions of themselves. Then also, if we need to, we can replace the drive motors to meet the design requirement. We are trying to put tracks onto the rover, but if those don't work out as we would like, an alternate approach would be to replace those tracks with wheels. In sensor failure, the alternate approach is just to replace it with an alternative, maybe a better version, or reconfigure the entire sensor suite to meet the objectives. Finally, concerning software and alternate approach, if we realize LabVIEW is not cutting it for the entire project or just portions of it, we could switch to C++ or the Python programming.
The references used for this project are the Procedia Computer Science article, Design of Mobile Robot with Navigation Based on Embedded Linux, by Azazi, Adrian, Atmaja, Handi, and Lucas. The International Journal of Intelligent Systems and Applications article, Mechatronics Design of a Mobile Robot System, by Mahfouz, Ali, and Salem. The Applied Mechanics and Materials article, Research and Analysis of Accuracy Location Estimation in Inertial Navigation System, by Rakowski, Siwalina, and Sadowski. International Journal of Computer Science and Engineering Survey article, A Kalman Filtering Tutorial for Undergraduate Students, by Rudy, Salguero, and Jalapa. Journal of Intelligent and Robotic Systems article, Estimating Vehicle State by GPS IMU Fusion with Vehicle Dynamics, by Saadaddin, Abdel Hafaz, and Jarrah. Programming Arduino with LabVIEW, Build Interactive and Fun Learning Projects, by Schwartz and Manicum, and LabVIEW Graphical Programming Cookbook, 69 Recipes to Help You Build, Debug, and Deploy Modular Applications Using LabVIEW, by Yang. This concludes the list of references. This concludes our presentation. We look forward to answering your questions. Thank you for your time.